Hello everyone, I am Shankar, faculty for Power Electronics and Control Systems at OHM Institute. In this video, I would like to discuss the questions from Power Electronics in the recently held exam TSSPDCL Assistant Engineer exam. Exam date is 30th April 2023. Now let us go to the first question given in the exam. There are four statements are given here. The circuit is a three-phase full converter. Now the question is, choose a wrong statement from the following three-phase full converter where the switch numbers 1, 3, 5 in the upper half, 4, 6 and 2 in the lower half. So as per the standard practice, the switch numbering is not changed. It is same as usual. There is nothing difference in this. But the only question here is, we need to identify wrong statement. Now if you observe the statements here, first statement, S1 conducts, S4 should not conduct. Okay. So that is basically correct statement, because in the three-phase full converter there is no freewheeling action. So this statement is corresponding to freewheeling action topic. Okay. So in three-phase full converter, the basic idea is there is no freewheeling action. When the freewheeling action will appear? Whenever the two switches from the same vertical limb are in conduction. So S1, and when S1 is conducting, S4 should not conduct. That is a correct statement, but we need to pick up the wrong statement. Next, when S3 and S6, here when S6 conducts, S3 should not conduct. So that is also correct. There is no freewheeling action in the full converter. When S2 conducts, S5 should not conduct. So that is also correct. Now what is the wrong statement here? When S3 conducts, S4 should not conduct. Okay, that is a wrong statement. Why? Because if you just recollect the conduction sequence diagram, say for example, if I take for alpha is equal to, of course, a particular firing angle is not given. If I say let us say firing angle is 0 degree, okay, then what is a conduction sequence diagram basically in this circuit? That is, sorry, at 60 degree S1 will start, at 180 degree S3 will start, at 300 S5. So before this also S5. At 120 S2, at 240 S4 and 360 S6. Okay. So in this particular conduction sequence diagram, what you can understand here, in this particular interval, that is from 240 to 300 degree, S3 and S4 both are conducting together. Therefore, the last statement, when S3 conducts, S4 should not conduct. This is a wrong statement. Okay. Hence, for this question, the answer is option D. Now let me read the question here. Each of 5 equal pulse widths in every half cycle of single phase inverter is pi by 15. So what do you mean by here? Each pulse width, each pulse width (2d by n) is given that pi by 15 radian. And how many number of pulses? It is mentioned that there are 5 pulses. So number of pulses, of course number of pulses per half cycle. So basically this is the question from multiple pulse width modulation in inverter circuits. Number of pulses per half cycle, n is given as 5. Input DC voltage is 100 volt. So let us take DC input voltage VDC is 100 volt. Then what is the RMS value of the output voltage? So here RMS output voltage VOR is equal to input voltage multiplied with number of pulses per half cycle, that is n, into 2D by n, each pulse width, divided by pi under root. Now by substituting these given data, 100 into root of 5 multiplied with pi by 15 divided by pi. So here you can cancel this 5 3 times and this pi and pi cancel, hence this value is equal to 100 multiplied with 1 by root 3. The numerical value will be 57.7 volt, and hence option A will be correct. Now let us look into the next question. A three-phase semi-converter is operating with a firing angle of 30 degree. What is the input displacement factor? So in this case the given data is firing angle alpha is given as 30 degree. Then input displacement factor, in the standard practice it is referred as displacement power factor, is equal to cos alpha by 2. So question is very simple, but the data is given in a such a way that you need a little bit calculations. So if you have a small trigonometric concept, you can do this problem. So basically from the trigonometry you can say that 1 plus cos alpha is equal to 2 multiplied with cos square alpha by 2. Therefore from this we need to find the value of cos alpha by 2. So let us substitute the values here. 1 plus cos 30, cos 30 is given by root 3 by 2, and hence right hand side I can take cos square alpha by 2, therefore I can divide here with 2 in the left side. Therefore what is the simplification here? Cos square alpha by 2 is equal to 2 plus root 3 divided by 2, okay, and 2 plus root 3 divided by, I am sorry, here this is a 4, this is 4. So cos alpha by 2 is equal to, if you take a root here, square root of 2 plus root 3 divided by 2, root 4 will give you 2 here, and hence for this question option A is correct. 2 plus root 3 under root divided by 2. Now let us look into the next question. The input power factor and displacement factor of an AC to DC converter are measured as 0.8 and 1.0 respectively. The input total harmonic distortion is, okay. Now here another little bit calculations. What is given? Input power factor. Let me write like this: IPF, input power factor, is equal to 0.8 and displacement factor, let us use a symbol dpf, is equal to 1.0. So from the basic relationship for an AC to DC converter, input power factor can be expressed as displacement factor multiplied with displacement power factor. So from this we can get distortion factor. Okay, input power factor is equal to distortion factor multiplied with displacement power factor. Therefore df, I can write it as IPF divided by dpf. This value you will get as 0.8. Now the relation between total harmonic distortion and distortion factor is square root of 1 by distortion factor whole square minus 1. Therefore if you substitute here 1 by 0.8 whole square minus 1, if you express in terms of percentage, this numerical value will come around 75%, and hence option C will be correct. Now let us look into the next question. If F is switching frequency and alpha is duty cycle ratio, then ripple voltage across capacitor in a buck boost converter is. There is a small assumption in this question, it is not mentioned clearly, but we can have a small assumption. So what is that? In buck boost converter, the peak to peak ripple voltage across the capacitor can be represented as delta V naught is equal to delta Q upon C, where delta Q is given by I naught multiplied with duty cycle ratio into cycle time divided by capacitor. But in the none of the option is having I naught and C, therefore I can say that the appropriate question wording should be the ripple voltage across the capacitor in buck boost converter is proportional to. Therefore I can select here, see in this case T can also written as D by F. Okay, so 1 by F. So let me say here I can give the answer, the ripple voltage in the buck boost converter is proportional to D by F, and hence I can select the closest answer will be duty cycle ratio divided by switching frequency, and hence alpha by F will be the most appropriate answer to me. This is a theoretical question, straight away you can answer it. So what is that? If IC, VGS, VCE represent collector current, gate to emitter voltage and collector to emitter voltage respectively of an IGBT. Okay, so the symbols have their usual meanings. Then the transfer characteristics is a plot of. So transfer characteristics either in IGBT or MOSFET will be the simply the characteristics between output current, in this case that is IC, and the control voltage, in this case that is gate to emitter voltage. Because if you look into IGBT circuit symbol, this is how IGBT circuit symbol. This is a gate, terminal, collector and emitter. So here IC output current, control voltage, gate to emitter voltage. Therefore IC will be taken on y axis, gate to emitter voltage will be taken on x axis, and hence option D will be the appropriate answer for this question. Next question, in chopper fed DC drives, so don't confuse with the word here DC drives, it's a basic application of any chopper circuit. Choose correct combination of quadrants. So the first observation from all these things, basically there are two choppers are addressing here, type C as well as type D. So before that, if you look into the quadrant characteristics of type C basically it will give you the quadrants of operations. Generally output current will be measured on x-axis and output voltage will be measured on y-axis. So in this case, type C chopper will give you the quadrants of operations, first and second quadrants. So basically in the drives field, what are these first and second quadrant? In the first quadrant, this operation is called forward motoring, and the second quadrant, the operation is forward regenerative braking. So type C chopper operates in quadrant 1 and 2. Okay, therefore I can say here type C operates in quadrant 2 and 3, this is wrong. Type C operates in quadrant 1 and 4, this is also wrong. Now if you look into type D circuit will give you first and fourth quadrants of operations. In this case also V0 on y-axis, I0 on x-axis, and of course not required for the question, but what is these quadrants of operations? These are in the first quadrant, just like earlier, it is forward motoring, and in the fourth quadrant of operation, reverse regenerative braking. Therefore type D chopper will give you the quadrants of operations in the first and fourth quadrants. So this is wrong and option C is correct in this case. Now let us discuss the next question. Identify one of the angles at which the average DC voltage equals to instantaneous output voltage of single phase full wave rectifier. So by observing this word, I have one concern here. It is not clearly mentioned what type of circuit it is. Full wave rectifier has different categories. One is a diode bridge, another is a full converter and semi converter as well. But by observing the output voltage waveform, we can consider that there are two possibilities here. One possibility will be single phase full converter with alpha is equal to 0 degree, or single phase diode bridge. So whatever the explanation I am going to give, that explanation is applicable for both of these circuits. Okay, so first clarification is that. Next, now for both of these circuits, the average output voltage, I can say VDC. Of course it is as it is mentioned VDC, otherwise let me use a normal notation, that is a V0. Average output voltage V0 is equal to 2 Vm divided by pi. So what is mentioned here, the average DC voltage equals to instantaneous output voltage of single phase full wave rectifier. Suppose if I equate this with Vm sin omega t, then by solving this equation you will have omega t is equal to sin inverse 2 by pi, sin inverse 2 by pi. So if you observe closely in the given waveform, at what angle this condition will match. So strictly speaking this condition will match at all of these points. Say for example, let me call this point is x, y Z and W. Okay. So at all these points the angle, this condition is satisfying, because instantaneous output voltage is equal to DC voltage at X, Y, Z and W. Now if you look more closely, this equation will satisfy at point X, but that option is not there. Next, Y, what is the angle? Omega t is equal to pi minus sin inverse 2 by pi. This answer is also not there. Next, at point Z, what is the angle? Omega t is equal to pi plus sin inverse 2 by pi. So whatever alpha is given in the options, don't confuse, that is not the firing angle. That is one angle, it is used some symbol alpha. Okay, don't confuse with that. Next, at point W, what is the angle? Omega t is equal to 2 pi minus sin inverse 2 by pi. Okay. Therefore, by seeing all of these values, I can say that the correct answer, the required angle will be option A, that is pi plus sin inverse 2 by pi. So with this, let me check any more question in the power electronics. All right. So these are the questions from power electronics subject. Now let me share my view on this paper, especially from power electronics subject, being a corresponding faculty here. So this from the last year onwards, even last year NPDCL exam also, paper is not so easy. In that, power electronics questions are not so straightforward like in the previous papers. So you need to understand the concept very clearly. Of course, these are not so difficult, but not so straightforward questions, just like a regular AE paper. Okay. So here I can say the difficulty level will be moderate to tough, right? And one question, if anyone is want to challenge this particular question, I will suggest the candidates, interested candidates can challenge this question, because these two parameters are not given in the options. Okay. Therefore, this is a good candidate, a good question for challenging the paper. Okay. So overall my view on the paper is, particularly power electronics, medium to tough or difficult. Medium to difficult questions are not so straightforward. You just need to understand the concept and waveforms clearly and apply some analytical things. With this, I will conclude this video, and we will meet in the next video, another video, to discuss control system questions. Thank you very much.